Welcome to the lecture series on transmission line theory. We are dealing with Smith charts. This is problem number 3. So this problem is based on finding unknown impedance with the help of a slotted line. So let us read the question out. So the question says the following two-step procedure has been carried out with a 50 ohm coaxial slotted line to determine an unknown load impedance. Step 1. A short circuit is placed at the load plane, resulting in a standing wave on the line with infinite SWR and sharply defined voltage minima as shown in figure 2.14a. On the arbitrarily positioned scale on the slotted line, voltage minima are recorded at Z is equals to 0.2 cm, 2.2 cm, 4.2 cm. Step number 2. The short circuit is removed and replaced with the unknown load. The standing wave ratio is measured as SWR is equals to 1.5 and voltage minima, which are not as sharply defined as those in step 1, are recorded at Z is equals to 0.72 cm, 2.72 cm and 4.72 cm as shown in figure 2.14b. Find the load impedance. And this is the figure which is given. So basically in this question, two different steps has been carried out to find the unknown load impedance. Okay, in step 1, a short circuit is placed at the load plane. So if you see here, the short circuit is placed at this particular point in this plane. In that case, the standing wave ratio is infinite and the voltage minima are sharply defined. So the value of standing wave ratio SWR is infinite and the voltage minima are sharply defined, as we can see from these figures. Okay. On a arbitrarily positioned scale on the slotted line, the voltage minima are recorded. So this is a slotted line section. This is the scale on the slotted line, which is arbitrarily placed, and on this scale the voltage minima has been recorded, and the recorded voltage minima are at 0.2 cm, 2.2 cm and 4.2 centimeters. Okay, now in step number 2, the short circuit is removed and replaced with the unknown load. So in step number 2, the short circuit is removed and it is replaced with the unknown load. So as soon as we remove the short circuit and replace it with the unknown load, the voltage minima are not as sharply defined as it was seen in step number 1. And the value of the measured SWR is now 1.5. In step number 1, the value of SWR was infinite. Why? Because the load was short circuit, which is 0. And in the case of unknown load, the value of SWR is given as 1.5. Why? Because the load impedance is no more short circuit, it is some complex value. So the voltage minima are not as sharply defined and they are recorded as 0.72 centimeter, at 2.72 centimeter and at 4.72 centimeters. Okay. Now given these measurement values, we need to find the load impedance, the unknown load impedance. Alright. Now let us start the solution. We know that the value of the voltage at any position Z is given by this formula, where this V0 plus is a constant, gamma is reflection coefficient, and this is the phase of the reflection coefficient. Now the maximum value occurs when the phase term, which is e to the power j theta minus 2 beta L is equals to 1. That means the value of the voltage V will be maximum when this phase term is equals to 1. Therefore, the V max is given by V naught plus times 1 plus mod of reflection coefficient, because this phase term is equals to 1. And the minimum value will occur when the phase term, that is e to the power j theta minus 2 beta L, is equals to minus 1. So V min is equals to V naught plus, this should be a mod of V naught plus times 1 minus mod of reflection coefficient. Okay, so in the question the value of V min is given, that is the position of V min is given in the question. Therefore we will use this particular condition. Now when do we get the value of this exponential term to be equals to minus 1? We can get that when the value of theta minus 2 beta L is equals to pi. Why is that so? Because we know that e to the power jx can be written as cos x plus j sin x. So whenever the value of x is equals to pi, we can write cos pi plus j sin pi. Now sin pi is equals to 0 and cos pi is equals to minus 1. So therefore this entire term theta minus 2 beta L should be equals to pi. Now if you rearrange this term, we will get theta is equals to pi plus 2 beta L. Now we are naming this L as L min because it is the distance from the load to the first voltage minima. Okay, all right. Now we need to first find the value of lambda. So we know that the distance between two voltage minima is given by lambda by 2. So in the question, in step number 1 as well as in step number 2, the value of voltage minima are given. So in step number 1, the voltage minima is given as, this is 0.2, this is 2.2 and this is 4.2. So if you calculate this distance, you will find that the value of lambda by 2 is 2 centimeters. Similarly for step number 2 also, the voltage minima is given. They are given as 0.72 centimeters, 2.72 centimeters and 4.72 centimeters. So if you find the distance between two voltage minimas, either you can find this distance or this distance. Both of this distance will be equals to lambda by 2. So in this case also, lambda by 2 comes out to be 2 centimeters. Alright, so we can tell that lambda is equals to 4 centimeters. Alright, now if you see this diagram, this is the most important point. This is the most important part of this problem. Now whenever the short circuit is placed at this point, we find that the voltage minima are occurring at these positions. But if you shift the position of the short circuit from here to here, then there will be no change in the position of the voltage minimas, because after every lambda by 2 distance the voltage minima is repeating. So we can place the short circuit at this point or the short circuit at this point or at this point. It will not make any difference. Okay, so let us say that we move our short circuit from here to this point. That is why I have made this line as the reference point, this blue color line, blue color dashed line as the reference point for placing the short circuit at the voltage minima position. Now in step 1, the voltage minima was measured at 4.2 centimeter and at 2.2 centimeter. And after replacing the short circuit, with the unknown load, the voltage minima has shifted to 4.72 centimeters to 2.72 centimeters. Now since we have changed the position of the load at this particular plane, now we can tell that the unknown load is placed here, somewhere here at this point, and the value of L min is the distance from the load to the first voltage minima. So this particular distance is L min, which is equals to 4.2 minus 2.72, which is equals to 1.48 centimeters. Now since we have already calculated the value of lambda as 4 centimeters, therefore we can write 1 centimeter is equals to lambda by 4, which implies 1.48 centimeter is equals to lambda by 4 into 1.48, which is equals to 0.37 lambda. So we have found out the distance between the unknown load to the first voltage minima, which is represented by L min, which is equals to 0.37 lambda or 1.48 centimeters. Now we can move to the Smith chart and solve the remaining problem. Now since in step 2, when unknown load impedance is attached, the value of SWR is given as 1.5. So if you see this in the radially scaled parameters, you can see this is the scale of SWR. So this is SWR is infinity, SWR is 100, SWR is 20, and so on. So from the center of the Smith chart, if you move radially outwards, you will find a point where the value of SWR is equals to 1.5. So using this as the radius of the circle, we'll draw a constant radius circle, which is also known as a constant VSWR circle. So using this as the radius of the circle, you can draw a circle which is your constant VSWR circle. Okay, now if you extend this line to this point, it will cut the VSWR circle here at this point. This point is the position of V min. Similarly, if you extend this line, it will cut the VSWR circle at this point. This is the position of V max. Okay, now in the question, the V min positions are given, so we are dealing with V min positions only. Now since we have found the value of L min as 0.37 lambda, so while moving from the V min position towards the load, we need to move in a counterclockwise direction. So as we can see here, wavelength towards load, it says wavelength towards load, and you need to move in this direction, that is the counterclockwise direction. So since this is the position of the V min, so from here, if you move 0.37 lambda all the way up here, you will find this is 0.37. Let me show you. See, this is 0.37. Okay, all right. So from this particular point, if you draw a straight line which connects at the center of the Smith chart, it will cut the VSWR circle at some point. This point will tell us the value of the load impedance, the normalized load impedance, which is 0.9 plus j 0.4. How do you find that? If you zoom in, you will find that the constant resistance circle which is passing through here, so it is somewhere between 0.9 to 1, that is 0.95, and the constant reactance circle which is passing through this point is 0.4. okay, so that is why the value of the normalized load impedance is given as 0.95 plus j 0.4 ohm. Therefore, you can find the absolute value of the load impedance ZL by multiplying the normalized load impedance with the characteristic impedance of the line, which is given as 50 ohms. Therefore, you can find that the ZL is equals to 47.5 plus j 20 ohm. Okay, so using Smith chart, we can easily find the value of the unknown load ZL. Now let us try to verify it numerically. Now we know that the value of reflection coefficient mod of gamma is given as VSWR minus 1 divided by VSWR plus 1. So VSWR value is given as 1.5 minus 1 divided by 1.5 plus 1. So this value is 0.2. The expression of theta is equals to pi plus 2 beta L. Now this L is L min. So this becomes pi plus 2 into beta is 2 pi by lambda. We have found out the value of lambda as 4 centimeters and the L min is 1.48 centimeters. So this value becomes 86.4 degrees. So the reflection coefficient gamma, which is mod of reflection coefficient times e to the power j theta, that is the phase of the reflection coefficient, we can write it as 0.2 e to the power j 86.4 degrees. So if you just expand it, you will get cos 86.4 plus j sin 86.4. So this turns out to be 0.0126 plus j 0.1996. Now if you put this value of reflection coefficient in the formula of the load impedance ZL, which is given by Z0 into 1 plus gamma divided by 1 minus gamma, it will turn out to be 50 into 1 plus 0.0126 plus j 0.1996 divided by 1 minus 0.0126 minus j 0.1996. So this turns out to be 47.3 plus j 19.7 ohms. So this is the value you have found out numerically using the formulas. And the value of ZL, which we have found out using the Smith chart, is ZL is equals to 47.5 plus j 20 ohm. So if you see these two values, they are approximately close to each other. Therefore, we can say that numerically also it is verified. Okay, so in this question we have understood that using Smith chart we can find the value of an unknown impedance, which was used as a very handy tool in the early days of microwave measurement. Alright, so I hope you have understood this question. This question is a very important question when it comes to understanding the problem of finding unknown impedance using the slotted line with the help of the Smith chart. Thank you very much.